Hi everyone, welcome to video number 2 for module 8 on models with a single categorical predictor. In the first module, we kind of addressed the concept of having categorical predictors and how we might want to code them. In this module, we're going to drill down a little bit deeper on how we actually calculate the slope and the intercept for situations where we're using contrast-coded predictor variables. Now, the situation is going to be a little bit different if you're not using contrast-coded predictors, but all in all, it's always going to be the same process where we're going to have models that create estimates which produce the smallest sums of squared errors, which means any formulas that we use in order to derive these estimates, they need to be predicting the means for each group in our categorical predictor situation. Right, so now when using these contrast codes, right, as we said, we had this example in the textbook where we have groups of people who either took an SAT prep course or did not take an SAT prep course, and then we got their subsequent scores on the SATs, and we're going to have a model A, model C comparison, right, where in model A we allow the slope to be some non-zero value, whereas in model C we force that value to be 0, right, which would be the same as excluding x from our model, because in model C we assume there is no relationship between taking this SAT prep course and the score you ultimately get on the SATs, whereas in model A we're allowing for that to be a non-zero value, and then by statistically comparing the reduction in error, we can make a statement about whether or not we reject or fail to reject the null hypothesis. So in order to fit model C, right, we have to actually decide how do we arrive at this value? Well, we said that the value that gives us the smallest sum of squared errors in any given situation is going to be the mean for a set of numbers. Okay, so for our estimate of model C, right, our y hat, we're taking this beta 0, this parameter, and we're actually fitting it, right? So beta becomes a b. B is a specific value that we actually get from our data, and we know that in the absence of any other information, we're going to want that to be the mean of all of the y's. And of course, the formula for the mean of y is just we take each y value, we add them together, then we divide by the number of values that there are. If you do that, you get 591. So for model C, we're estimating y as a function of 591 plus some error, right? So here are our actual y values, people's SAT scores. Everyone gets an estimate of 591 because we're estimating the same constant for each person. And then we get errors, right? And then by squaring those errors, we can calculate the sum of squared errors. Model A is a little bit trickier, right? And the formulas, I think, can throw you off a little bit at first. But when we're using contrast codes, one of the reasons that we like contrast codes is they actually allow us some computational shortcuts in these situations, where we're going to have a model A, right, where we have y is a function of an intercept plus a slope times x. Oops, and actually there should be a plus sign here. That's plus error. It's not multiplied by the error. But what we have to do, right, is take these parameter estimates and fit them in the data. That is to say, we have to turn them from betas into b values, which are actual numbers, right? So in order to take this beta 1 and get b1, what we're going to do if we have contrast-coded predictors is we can take the code for each group multiplied by the mean of each group, and then we can add those two values together. So in our case, we have a mean of 577 for our people who didn't take the course. That was their average SAT score. And we'll multiply that by the code for that group, which was -1. And then we'll add to that, right, because we're summing. We add to that 1 times 605, because 605 was the mean of the SAT scores for people who took the course, and it's getting multiplied by 1 because that was the code for people who took the course. So that's -577 plus 605, and then we divide that by the sum of the two codes squared. So we have -1 squared is 1, plus 1 squared is 1. So adding those together, we get 2. So the difference between our two group means is 28, and the sum of the squared contrasts is 2. So we have a mean difference of 28 divided by 2 gives us a slope of 14, right? And this is important because this slope, when we have our groups coded as -1 and 1, is always going to be half of the mean difference, right? Because we start with some intercept, and then we're going to go up by 14 points when x is positive 1. We're going to go down by 14 points when x is negative 1. So 14 is half of the difference between the two means, right? And to get the full difference between the two means, we have to go from negative 1 to 0 and from 0 to positive 1. So to get the full difference between the two means, that actually requires a 2-unit change in x, assuming that we've coded these things as negative 1 and 1. But that's how we get the slope of 14 in our equation that ultimately is going to give us a mean for each group. We can also then solve for the intercept here, right? So again, we have a beta 0, which we need to turn into a b0. So in order to fit this b0, we're going to take the sum of the mean in each group. Okay, so this is y bar sub k. So this is the mean for each group. So again, that's going to be 605 for our course group and 577 for our non-course group. And then we're going to divide that by the number of groups that there are. So we have 605 plus 577 divided by 2 gives us 591. So 591 becomes our intercept, right? And that is right in the middle of our two groups. So this is the mean of the group means. It also happens to be the mean of all the data in this situation because we have equal numbers of people in each group. So in a balanced design, the intercept that we get here in model C, right, and the intercept that we get here in model A will be the same because we have equal numbers of people in both groups. That won't always be the case. When our means are not equal, right, this won't necessarily be the mean of all the numbers, but it will always be the mean of the two group means. Okay, so that's important. So 591 is the mean of the two group means, and then if we're in the course group, we're going to add 14 to that, right? We go up by 14 because we're multiplying it by 1. And if we're in the non-course group, we're going to subtract 14 from that, because if you're in the non-course group, we're going to go down by 14. So these two coefficients, right, our slope and our intercept, are ultimately going to give us a model that makes one prediction for the course group and one prediction for the no course group. And specifically, it's going to predict the mean for everyone in the course group, and it's going to predict the other mean for everyone in the no course group. And if we're predicting the mean in each group, that gives us the smallest sum of squared errors within each group. And then when we add those sums of squared errors together, we get a new total sums of squared errors, which we can compare to the sum of squared errors from Model C. And again, if the sum of squared errors is significantly reduced, we would conclude that Model A is the better model, and we would reject the null hypothesis. So in practice, we're going to get statistical programs to obtain these parameter estimates for us. However, I think it is important to understand how these parameter estimates are obtained and how we should interpret them based on the coding of our variables. The book focuses on contrast-coded variables, and we will focus on contrast-coded variables throughout the course for a number of reasons. But dummy codes or treatment codes, right, in which one group gets a 0 and another group gets a 1, are valid methods of coding, right? You will arrive at statistically correct answers if you treatment code your variables rather than contrast code them. But contrast codes offer a number of computational advantages in that we can get these slopes and intercepts a little more easily, right, if we use contrast codes. The formulas we just showed in the last slides are pretty short, if not, even though they're not necessarily intuitive. And they also offer interpretational advantages because oftentimes, especially as we add multiple variables to our models, we might want to evaluate one variable on average across the other variables, right? So in a lot of situations, we'll want to know what's happening for the average person or what's this effect on average. Contrast codes allow us to do that in the same way that mean centering of a continuous predictor allowed us to do that in some of our previous models. Now, the other thing that I want to clarify here is that we're talking about a t-test in this situation. Now, I wanted to make a distinction between a t-test and what is sometimes thought of as the t-test, because often, especially in undergraduate courses, the t-test, right, is taught as a specific test that is only ever used for comparing the mean of two groups. And this either implicitly or explicitly leads students to think that t-tests are something that is different and distinct from regression. However, we've just done a regression in which we compared the means of two groups using a t-test, right? So what is it? Is t-test different from regression, or is it the same thing, or how does it work? Well, as we've shown in some of the models we've built throughout the course, we can conduct a t-test in any situation where we have a single degree of freedom in the numerator, right? So using the general linear modeling framework, we can use a t-test anytime the difference in the parameters in model A and the parameters of model C is 1. If it's greater than 1, we'd need to use an analysis of variance and an f-test. But we can always do a t-test, right, anytime PA minus PC is equal to 1. So this means that we can conduct a t-test for an intercept. We can conduct it for the slope of a continuous variable, as we have done before, and we can conduct it for the slope of a categorical variable in order to ascertain the difference between two group means. So this is something I want to emphasize, in that in some statistics classes, all of these analyses are taught as separate and distinct entities. In reality, they are variations of a general linear model, right? And this is a little more complicated, it's a little more nuanced, but it gets us to think a little more deeply about the data and what models do we actually need to use in which situation, because these tests we can actually use for statistical inference in a lot of different situations. And as we'll see, we can, as we have seen, we can get t-tests for lots of different types of effects. We can also calculate the f observed from an analysis of variance for lots of different types of effects. And so this gives us a little more freedom, but it forces us to think a little bit more carefully and recognize that independent samples t-test, dependent samples t-test, one-way analysis of variance, factorial ANOVA, all of those terms that you might have heard in other contexts or in other stats classes are really just different implementations of general linear models.